Today is we're dealing with sections 11.2 and 11.3. Section 11.2, we're doing two sample hypothesis testing for dependent samples, also known as matched pairs. And so as we go through our hypothesis testing, our significance test, we're trying to see an observed difference in sample means can reflect an actual difference in the parameters. So as we compare mu1 and mu2, or it just may be due to a chance variation in random sampling or random assignment. The null hypothesis has the general form of mu1 minus mu2 equal to whatever your hypothesized value is. So it may be that hypothesis value is a certain number. Typically, when we're doing this comparison, we're trying to state that there is really no difference. And so the difference between the two things is zero. So a lot of times we're going to see our null hypothesis set up where the two mu's are equal to each other, or that mu1 minus mu2 is equal to zero, that the difference between the two things are zero. There's no difference between them. The alternative hypothesis is what kind of difference do we expect? Is it greater than? Is it less than? Is it not equal to? And so again, when we're looking at this statement here, we have to read what are they looking for? Is it different? Is it less than what we expect, or is it greater than? And so I have an example of some of the things written down below. Again, we don't have to do a lot of this formality stuff of writing, what type of test are we doing in our course? But this is how our null and our alternative hypothesis are typically set up. We're looking at the first statement, you have one of two options. But for the alternative hypothesis, you're picking on, basically your inequality symbols there. So we always have to make sure we define if we're using scripting, what the mu1s and mu2s, what do they mean? Our plan as we go through is to do a two-sample t-test, is what we're going to do here. So we'll find that code in the calculator to do it. We're doing basically matched pairs. And we're going to see an example, and it'll make more sense when I show you what does matched pairs mean. We have to show our conditions. Do we meet the conditions of random? Our normal, that's where it's a little bit longer. We learned about the normal conditions with the less than 30 process. We have to go through and graph. So if both samples are greater than 30, fantastic. Then we can say they're approximately normal. If the sample is not larger than 30, then basically we have to graph both samples. So that's where we're doing the normal probability plot. And then we're also doing a box and whisker. Again, here in the normal probability plot, we're looking for a nice linear pattern. And the box and whisker, we're using that as a double check for outliers. Do we have outliers? So I'm going to walk you through. Now, in order to do this portion right here, they have to give us all the data values. All right, if they just give us statistics, they tell us that the means and the standard deviations are certain numbers, then we really can't do this part. So they're going to have to give us some stipulation that, hey, conditions were met, the normal conditions were met, or any of the conditions were met for the process. If they give you all the data values for both for the thing, then we get to do the graphing aspect. When we're doing the independent again, this is our little 5 times our sample size. Is it less than the population? That's that little stipulation. And it has to be for both of the different, if you're doing 2 different samples, both of them, N1 and 2, both have to be that way. So those are the conditions that we have to always make sure we double check before we do the process. We'll get some practice doing that here in a little bit. And so now I have an example kind of queued up. And what I had would just say, why is this a matched pairs? Okay. Because that's the first thing is what's the difference between a matched pair or a 2 sample? A matched pair is basically when you're taking, in this case, it's each individual student, and you're doing, you're in this activity, what they're doing is trying to check their reaction time with their dominant hand and their non-dominant hand. And so it's the same student being used in two different processes, okay, two different trials. And that's why it's a matched pair. We're going to compare, the reaction time between their dominant hand and their non-dominant hand. Another example, Eliza, I bet you probably already did this and probably Ellie as well, because you guys are both in the host program. I bet you in those classes, you guys did a standing and resting heart rate activity. Mm-hmm. All right, so when they're comparing your standing and resting heart rate in those activities, that's the same thing as if you're doing a matched pair, is what that is. Because you're saying, okay, what's my heart rate standing? And then they have you sit down, they do it, and then we say, okay, what's the difference? And then that's a matched pair activity. So when you're taking one sample and you're putting it through both treatments, if you want to call it, then it's a matched pair. If we get two totally different things, if I take the sample, your guys is just sitting heart rate right now, and then next block I take my AP kids and take their sitting heart rate, that's two different samples. Okay, it's not the same person being used twice. We have the same number of people, it's just we have two different samples, and that would put us what we call a two-sample t-test that's not classified as a matched pairs, because there's two different samples that we're comparing. Whereas here, we're comparing you guys, where this one sample is only collected once. There's only one sample collected. So, as we do this, Professor Andy Neal measured the time in seconds required to catch a falling meter stick for 12 randomly selected students, dominant hand and then their non-dominant hand. Professor Neal wants to know if the reaction time in an individual's dominant hand is less than. So there's our alternative hypothesis, right there. He wants to know if the reaction time is less than, if the individual's dominant hand is less than the non-dominant. So as I think about eventually writing my test for my null hypothesis, the mean of the dominant, actually that'd be my, hold on a second. This one's going to be easier to write the alternative one first. So the mean of the dominant is less than the mean of the non-dominant. So mean of the dominant is less than non-dominant. In the null hypothesis, we're always doing a statement of equality, and in this case, we're going to say that there's no difference. So is mu of the dominant equal to the mu of the non-dominant? And again, that's one way you can write your hypotheses. We can also write them as mu dom minus mu non-dom, or non. That's equal to 0. So we subtract the non-dominant over. And then in this case, mu dom for the alternative is minus mu non is less than 0. So those are the two different ways we can write our hypothesis statements. Now, when we go to type it in the calculator, I'm going to write down some numbers real quickly. I have that column already done for you, but I can show you how to do it from scratch. We only want to run our test this last column. So here I have it stated up above. We're trying to do our test based on mu d, and where d is equal to the difference between dominant and non-dominant. So I went through and did this on the calculator earlier. I went in and put the non-dominant in L1, the dominant in L1, the non-dominant in L2, and I told in L3 for it to go ahead and subtract it. These are the answers I got for this column here. So if you can join with me, just write these down. Because all we're going to do is type these numbers into the thing to make it go a little bit quicker. And again, if you can't read one of my numbers, please let me know. All right, so we're just going to type that column into our calculator. And the reason why, and I'm going to put this back up there for you. The reason why we got to type it in there is because have we checked any conditions yet? You know, we haven't checked, so I wanted to walk you through on the graphing aspect. How do you check the normal probability plot? How do you do the box and whisker plot? So I wanted to walk you through that aspect. So what I'm going to do is I'm going to get in there and I'm going to just type in this one column. I'm going to type that in and I'm going to use column L1 to do it in. Because I didn't put the other stuff in L1 and 2, so that's why I'm not going to use L3. So stat, go into edit, and then carefully type in those numbers. Because we're going to show you how to do the normal probability plot. All right, so I got my numbers in there. So they did tell us that there was a random sample. When we look at our conditions, random sample, they told us that we had a simple random sample of 11 students, right? Oh, 12 students. Okay, I'm off a number. Daggone it. Who did I leave out in my table? Okay, got you. 005, 0001, 003. Yes. All right, so what did Mr. Stevens? All right, somewhere I'm off one. I gotta be missing. It's got to be this one here. That's a negative. What's 197, 172. 5. All right. My apologies on that one. I had all the cells next to it, so I thought I had the right amount. Obviously I didn't draw my table on the right long enough, and to add up an extra column there. So I have all my data values there. We have a simple random sample of 12 12 students. 12 is less than 30, so we need the graph for us to do the normal part. So does anybody need more time typing numbers in? All right, so on your calculator, we're going to go second y equals. We're going to go into plot 1. We're going to press enter on. And then I'm going to arrow down and I'm going to do the very last graph on that line. That's the normal probability one. So I'm going to press enter. I have my data in L1, so I'm going to leave it alone. And then now I'm going to hit graph. I see it's all jumbled up, so I'm going to do a zoom 9, so it zooms in on the statistics. So this is what I'm drawing, and just to decide, okay, is this approximately normal? So I'm just going to draw a rough probably a little bit too much of a steep there, but that's about it. So as we look at this plot and I draw a line, if I draw a diagonal line, that's not bad. Okay, it's approximately linear there. And then now, once we do that, we need to look at. I don't see any outliers from that picture. I do see some changing, so I think there's some slight skewness in there. But I want to take a look at the probability plot, and let's take it, or the box plot, and let's take a look what that looks like. So if I go second y equals, and I change my graphing to the fourth one, the one with the 2 dots, that's a probability. That's a box and whisker plot that actually has outliers. For it to indicate what the outliers are. So I'm going to press enter. I'm going to go back to hit graph. And then when I look at the box plot, and to me, this is why it sort of makes sense why I see what I see. And we talked about how wide, what does it mean when you have short and long parts of the whiskers and inside the boxes and so forth. And so when I look at this, there's a lot of data here. And there's a lot of data in kind of this area because again the whisker is short. And again, we're more spread out in these 2 parts. So we can say there's some slight skewness, but there's really not any strong skewness. So we do. I mean, I think there's some. That's why we see this kind of curving pattern go with what we see over here. We see that little curving going on because of what this is doing here and there, and as we look at it. So I see a little bit of slight skewness. But no outliers. So approximately normal. If we had an outlier where one of the dots was really far away from the rest of the dots, then we would say, hey, we got an outlier, so we probably wouldn't want to do the normal probability here. But right now, there's not enough information to really hold me back from doing it. So slight skewness is okay, especially when you're in the mid-teens or close to the mid-teens with no outliers. So we're gonna stick with that. And then the last part is that independent part. If I have 5 times 12, that's 60. We would say reasonable to assume more than 60 college students. So we do have, we meet the independence clause since we're not doing sampling without replacement. So we're going to go ahead and proceed with our test. So we're going to do a t-test for matched pairs. Now, the matched pairs is not on there, but this is where we're just using the D column is all we're using. So I'm going to go into stat, go over to test. We're going to go down to t-test. I'm going to pause here. We're going to use the option that says data because we typed in all the numbers. Okay, so I'm going to use the option that says data there. My data is in L1. In this case, my null hypothesis, we said that it was equal to 0. If we go back up to our hypothesis statements, we said that in our null that it was equal to 0. So my null hypothesis is 0. I would say most of the time it's going to be that. But again, each problem could be a little bit different. If they're going to state that the difference between 2 things is exactly another number, then we put that number there. So my stuff's in L1. So my list is L1. Again, as I look at my alternative hypothesis, we used to where it was less than. So I want to choose less than mu naught is what I want to choose. So I want to go down here, choose the middle option. And then we're going to go down to calculate. And this gives me a test statistic. of negative 2.7759 and a p-value of 0.0090. And then they asked me to make a decision. So since 0.0090 is less than 0.05, we reject the null hypothesis. There is convincing evidence. I'm going to get rid of the calculator so I can put that on the screen more. There is convincing evidence to support the claim that a student's reaction time with their dominant hand is less than the reaction time with their non-dominant hand. I'll give you a chance to make sure you get that there. So there's our conclusion. Again, he was thinking, he was testing the hypothesis. Hey, we do have evidence based on the data there that the student's reaction with their dominant hand is less than their non-dominant. So, when we think about it, we do a lot of things with our dominant hand. So we would think our reaction time, or at least for most of us, would think, hey, that should be faster. Because it's like, hey, it's my one hand that I like control the most. He has a hypothesis that he thinks that it's less. Then now it opens up for further studies. Okay, why? Why is the reaction time with the non-dominant hand faster? Is there a reason? Yes. All right, let's go. I'm curious as to what all those numbers are. That's supposed to be okay, so that's just that last one. There we go. Yeah, just one little data point to throw that thing off of. A lot. So, all right. So there's our decision. Again, I've got a couple more problems in here for us to do. They asked us to construct a 95% confidence interval for the mean difference here. So again, all conditions were met. So we can go ahead and do this. There's a lot of connections between a two sample confidence interval and hypothesis tests. You don't do it with one sample stuff. But with two, there are some connections between the two. So all conditions met. So let's do our 95% confidence interval. So we're going to do a T. We're going to do a T interval. Is what we're going to do here. So as I go back in, stat over the test, I'm going to do option number 8. Is what I'm going to do. Option number 8, T interval. Again, we're going to use data. We still have our data in there, so we're still going to use our data from L1. And all we want to change here is, well, we don't have to change it. They actually tell us that we want a 95% confidence interval, so but mine's already set up that way. So we can just go down to hit calculate. And we get negative 0.0236. And negative 0.0027. So when we write those phrases, when we write our conclusion for that one, we usually say something like, we are 95% confident that the interval from negative 0.0236 TO negative 0.0027 captures the true mean difference between reaction time with dominant hand versus reaction time with non-dominant hand. And then here's where we get to make the connection between the two things. Since 0 is not in the interval of negative 0.0236 to negative 0.0027, there is convincing evidence to support the claim that there is a difference between dominant and non-dominant. So, I'll give you a chance to write that. Again, we don't get to make these connections between a confidence interval and a hypothesis testing when we're dealing with one samples. Well, when we're dealing with two samples, and we did this with proportions as well, if the hypothesized value for the difference is in the interval, then there's not convincing evidence. If the hypothesis value, like in this case 0, is not in the interval, then there is evidence. And so this just gives us extra, support for that. Hey, what we did here with the hypothesis that was true. It gives us extra evidence for it. You can only use the confidence interval based on the alpha value of your hypothesis test. So since we did a 5% alpha, 1 minus 5% is 95%, so we have to do a 95% confidence interval. So we can only compare those two with each other and stuff, and that's where it backs it up. And so I have two more problems on this section than I have some with two separate samples. So when we do independent samples, as we look at it. So the next one, naughty or nice, and I have it kind of broken up in stages here. An experiment was conducted in which 16 10-month-old babies, so N is 16, I'm just going to write that down, N is equal to 16. 16 10-month-old babies were asked to watch a climber character attempt to ascend a hill. On 2 occasions, the baby witnesses the character fail to make the climb. On the 3rd attempt, the baby witnesses either a helper toy push the character up the hill or a hinderer toy that preventing the character to make the ascent. The helper and hinder toys were shown to each baby in random fashion for a fixed amount of time. In problem 41 from an earlier section, we learned that after watching both the helper and the hinderer toy in action, 14 of the 16 10-month-old babies preferred to play with the helper toy when given a choice as to which toy to play with. A second part of the experiment showed that the climber approached the helper toy, which is not surprising. And then alternately, the climber approached the hinder toy, which was the surprising action. The amount of time that The 10-month-old watched the event was recorded. The mean difference in time spent watching the climber approach the hinder toy versus the climber approach the helper toy was 1.15 seconds with a standard deviation of 1.5. They asked us to state the null and alternative hypothesis to determine if babies tend to look at the hinder toy longer than the helper toy. So we got our null and alternative hypothesis. Sorry, you guys use a 1. So in our null hypothesis, we're saying that it's equal. So I'm going to say mu of the trying to use I'm going to say mu1 equals mu2, and I'm going to state over here mu1 is equal to the helper toy, and then mu2 is equal to the hinderer toy. I thought about using the H's, but that didn't help. Again, they ask us to, in the alternative hypothesis, that they looked at the hinderer toy longer. So that would be mu1 is less than mu2. So helper is shorter than yes, helper is shorter than the hinderer. Now on this one, they tell us that this number right there, that's our X bar. That's X bar. X bar is 1.14. They tell us what the difference is. And the standard deviation is 1.75. So now as I go through, assuming that the difference is normally distributed, so again, they didn't give us data values, so we have to, they have to give us that statement that, hey, we met the conditions, so we can go ahead and do the stuff. And they ask us that it is great, is the difference, will it be greater than 0? Okay, so as I set up my hypothesis test, as I go into the calculator, as I clear the screen, we're going to go over to test. We're doing a t-test is what we're doing. A t-test. Now, when I choose the t-test here, they didn't give me all the data, so I have to switch it over to what they call stats, to where I can actually put in I can actually put in the mean and the standard deviation. So I got to choose stats. I have to type in the mu naught. Mu naught again would be there is no difference, so 0. Ah, crud. My apologies. They told us that the mean was 1.14. Standard deviation was 1.75. And we are, so X bar was 1.14. S sub X is 1.75. Again, we are choosing that it is less than. So we want to keep with that middle thing. Sample size was 16. So N was equal to 16 because they said there were 16 10-month-olds. And then we're ready to hit calculate. And here I get that my T statistic is 2.6057. And my p-value, that is a really big p-value. Let's make sure I didn't make a goofy mistake. We're going to double check that one. That's just a really big p-value. And then I think I realized where I made my goof mistake. We're trying to say that it actually, we said that it was greater than. greater than the mu, so greater than 0. So I need to actually say greater than the null part. So that's where I made my mistake. I'm not sure if you guys followed along or if you ignored me on there. So let's go back in there and change that to be greater than 0. So that's the one I want, is greater than. All right, so that's going to change my p-value. My statistic should stay the same. It's the p-value is what should get changed on that one. So 0.0099. So again, here we would say the same thing. Since 0.0099 is less than 0.05, we reject the null hypothesis. There is convincing evidence to support the claim that 10 months old the difference in the amount. So that the difference in the amount of time the baby will watch the Hinderer toy is greater than the helper toy. All right, so we do have evidence to support that. There's a follow-up question about the behavior. What does it imply? So that was one thing I was going to ask you all, is like, what do you think about the results of this experiment apply about 10 months old's ability to assess surprising behavior? This is one of those ones where you got to come, there's not one exact set right answer. But what's one interpretation that you can say here? They are, yeah. I think they are able to assess surprising behavior. Then I'd ask the follow-up question. So what does it mean if they watched the Hinderer toy more than the helper toy? What does that imply about characteristics for the baby? They're attracted to the toy that isn't helpful. It's kind of stopping, and reach the goal of ascending the hill. So is it a thing where they like seeing that adversity take place, to see that struggle? Those are the kind of the follow-up psychological things you could ask in a study. What's causing them to be drawn more to that aspect. So again, a couple different things you can do on that one for answers. Last one in this section, they say we have in the bottom table here at the bottom, it says we have the muzzle velocity in feet per second of rounds fired from a 155 millimeter gun. For each round, 2 measurements of the velocity recorded using 2 different measuring devices. Which of the with the following data that was obtained? Why is that a matched pair? So they want you to say, okay, why is that considered to be matched pair instead of, because we see 2 different lists, A and B. Why is this considered to be matched pair as opposed to two separate samples? Same gun, and then what? The fired bullet, 1. And and they recorded the speed with one type of device, but on that exact same bullet, they used another type of device to record the speed. So they're using the one sample, but measuring with two different things. And so they didn't take like, hey, let me just shoot one and then compare it with another one shot and record it with the other one. At the same time, they use the two different devices. So that's why it's kind of the match pairs. There's only really one set of data here. There's one set of data. There's one set of data being measured by two different devices at the same time. And then the next part, they said, is there a difference in the measurement of the muzzle velocity between device A and B? They told us to use an alpha of 0.01, so we finally changed an alpha of 0.01. The normal probability plot shows, and a box plot says that things are approximately normal, so we do not have to go through and draw those things. We don't have to worry about it. And then they asked us to construct a 99% confidence interval as well. So now all we got to do, they do ask you to draw the box plot, but I'm assuming that you guys will be able to draw the box plot. What we need to do quickly is, because I didn't set this one up yet, let's get into our table. And let's go into column 1. Let's put A in column 1 and B in column 2. So carefully type those things in there. Again, you do need to make sure that you pair them up correctly, because we're trying to make sure we subtract the right values from each other, the associated values from each other. All right. So I got my stuff in L1 and L2, and then in L3, I'm going to set it up to where it does L1 minus L2. I'm going to double check, is that the way they want me to? Is there a difference between A and B? So we're just going to do A minus B is all we're going to do there. So in L3, we're trying to find the difference. So I'm going to go back up to the column header, tell it to do L1 minus L2 in the column header of L3. And then that's the column I'm going to run my hypothesis test on. Again, we don't have to, if we were graphing, doing the box plot and normal probability plot, that's what we're doing the probability plot and the box and whisker plot on, is that column right there. Checking to see if it's approximately linear, there's no outliers. Again, they told us it was okay. Is it okay if I move on to the test? I want to make sure that, don't know if I'm going too fast or not. So I go over to test, down to t-test. Again, we used data, we typed in numbers, so I'm going to go back to data. Again, we're going to say in the null hypothesis that there's no difference. So we're going to leave that alone. My data is in L3, so I'm going to change that to L3. And now we didn't write our hypotheses here, so my null, of course, that it was equal to 0. So mu A minus mu B equals 0. What do I need to write for my alternative hypothesis? What inequality sign should I use? Do they lean one way or the other, saying greater than or less than? They don't. So this one right here, is there a difference? That tells me I need to use a not equal to symbol. So that little part right there, is there a difference? That tells me I need to use the not equal to symbol. So our T statistic, again, was 0.8517, and our p-value is 0.4125. Well, that blew 0.01 out of the water. All right. That's greater than 0.01. It's greater than all of it, so we failed to reject. The HO, there is not evidence to support claim. So there is not evidence to support the claim that there is a difference between the two devices measuring the velocity of the muzzle. Okay. So there is not evidence there. Now, what should happen here when we go to do the confidence interval, 0 should hopefully be in our confidence interval. And that would support what we're doing. Okay, because on the other one, the previous one, when 0 wasn't in the interval, there was evidence to support the claim. So hopefully when we do our confidence interval for 99%, 0's in the interval, which would support that, hey, there's not convincing evidence. Okay? So let's see if we did that right. Because it should coincide when we do it. So go over here, test down to a T interval. And again, I'm using data. I got to change my data is in L3, so I need to go through and do 0.99. Hit calculate. And my 99% confidence interval is negative 0.3088, comma, 0.54209. So yes, 0 is in the interval. So we failed to reject. There is not convincing evidence. Okay. So that wraps up the dependent sample, is what that wraps up. We're going to go quickly into the other one, and it's really the only difference is we have two separate samples. We're not using one sample used two different ways, like we did on this one with the two different devices, or when you look at the dominant hands left, and so forth. Here we're going to have two separate random samples. So, so as I get rid of the calculator and we kind of go back over here,